Hello and welcome to Aughton Math. Today we're going to talk about linear functions and models. So we're going to handle modeling word problems with linear equations. Before we get into that, let's talk about different ways to write functions and relationships between variables, in this case linear equation. So I just want to introduce, and this should be a review, f of x we can consider as a value for y. So the function of x, in this case, some function, it can be a linear equation or some other function, and I'm going to ask you in the homework and some other potential problems on the test to find the value of a function when the value of x is equal to 2, or a value of x that can be any value given a certain function. So the command here is I have a function where I substitute some value in for x and then resolve or solve that function to provide an output which is a value for y, or the function of x. So in this case, if the function of x where f of x is equal to 2, where x is equal to 2 in the function, the command is going to be to substitute 2 for x, and then to simplify that function, 3 times 2 is 6 plus 2 is equal to 8. So f of 2 in this case, where f of x is equal to 3x plus 2, ends up being equal to 8. All right, so let's do some classwork. So if f of x is equal to 5x minus 10, find f of 3, f of negative 3, find the 0 of f, graph f of x, and then find where the 0 of f of x is. All right, so I gave you a moment to find those answers, and I'm going to display them to you, and then we're going to graph the function. All right, so f of 3 is plus 5, so 5 times 3 is 15 minus 10 is 5, and f of negative 3, negative 15 minus 10 is negative 25. Find the 0, so the value of x that makes f of x equal to 0. So f of 2 is equal to 0. Let's graph f of x. So where does it intersect the x and y axis? Well, it intersects the y-axis where x is equal to 0. So 5 times 0 is 0 minus 10. So the graph intersects the y-axis at 0, negative 10. And where is the 0 of f of x? So what we want to do is we want to find it really should say the x-intercept, and that's going to be 2, 0. All right. So then we're going to graph it. We have the 2 points, the x and the y-intercept. We have a consistent rate of change, or a consistent slope between the 2 points. And as you notice, this is similar to the form y is equal to mx plus b. So in this case, the slope is 5, y-intercept is negative 0, negative 10. All right, so let's just take what we've evaluated and ask, what's the defining aspect of a linear equation, or what do we need for a linear function? And I'm going to answer those questions for you. First and foremost, we need to have a consistent slope between any 2 points on the function, so steady growth or decline. So it's going to be a line with a constant slope, and then we need some output value, and then 2 variables, x and y. So when you're writing a linear equation, you need a point and a slope, but for a linear equation we need to have some steady growth or a constant slope between any same slope between any 2 points in the function. All right, so we're going to work with tables here. I want you to take a moment and evaluate values for L given values for T. So the input value is T. This is the independent variable. Dependent variable is L. So this is temperature and length in meters of some object that's growing or expanding as the temperature increases. All right, so these are some of the values you should get, at least for the first 3 blank areas. 10 plus 10, 0.0001 times 10 leaves us with 10.001, and then 20, 10.002, 10.003, and so on. So you can see that there's some input here, the x value, independent variable, output is the length. And then we can graph this. We see we have a constant slope of 0.0001, and then a y-intercept is 0, 10. All right, so now the next question is, can you create an equation given these values, so input 300, output 120, etc. I'm going to pause while you figure that out. and you should end up with c is equal to 0.4 times the distance. Now, what we want, this kind of leads you into imagining that the relationship between input and output is always going to be 0.4, but what we are measuring really is the slope of the line, and that relates to the change between the y value over the x value. So y value here is the cost, x value is the distance. So if the slope is the same, and it is in this case, it's 0.4, then we have a linear equation. But it also so happens that the distance multiplied by 0.4 ends up being the cost. And it doesn't always work that way. When you're measuring a point, you have to take a look at the change between the points in order to figure out the slope here for future equations. All right, so now I'm going to change things up a little bit. I've changed some of the numbers. Now I want you to evaluate this particular function. First, determine if it's a linear function. Right? I have same rate of change. The slope is the same between points. And then, given that, can you create a linear function to model this particular problem? So I'm going to pause here while you do that. All right, so you're going to end up seeing that the change between cost over distance ends up being 0.4 again. And then if you are to evaluate this using the point slope formula, so we find out the slope is 0.4, and then we use a point. We can say 130 and 300, and use a point slope formula, y minus y1, which would be, let's say, c1 is equal to the slope, which we figured out to be 0.4, times x minus, in this case, d1. And really we should say d minus d1. So I'm switching the variables here. And then you'll evaluate it right in slope-intercept form, and then you'll come up with this answer, c is equal to 0.4d plus 10. All right, so let's take a look at another function. I'm going to ask you if this is a linear function. I'm going to pause here while you figure it out. And then you'll see that there's no constant rate of change. The slopes between the points is not the same, so we can't call this a linear function. Let's move on to another problem. All right, so let's figure out if this is a linear function, and then let's go on to see if we can write an equation to model this function. All right, so yes, it is a linear function. The slopes are the same between all the points. So we're going to figure out, so change in d over the change in c is constant. We could also say the slope is the change in c over the change in d. That's really the slope here. And that's constant. All right, so we're going to define our independent and dependent variables. We see that x is the distance in miles. That's the independent variable. Y is the cost of the distance traveled. So we want to find the change in c over the change in d, and we're going to evaluate that. We figure out that that's 0.3. We can use this first change here, 140 to 260, 400 to 800. All right, so now we're going to use a point slope form to write an equation, and we can just select one point. So c minus 140 is equal to 0.3 times d minus 400. And then we end up with the equation y is equal to 0.3d plus 20. So again, we're finding the slope, cost over distance, change in cost over change in distance. So it's the difference between the 2 points here. And this would be a point. This would be a point. But in slope, we're measuring the distance or the change between the 2 points. All right. So again, this is just the math behind that problem. And the next step is to apply what we know in the problem to an extension question. If the driver could spend only $475, how far could they travel? So we're going to say distance traveled 475 is equal to 0.3. I'm sorry, cost is 475 is equal to 0.3 times the distance traveled plus 20. We evaluate for D. We end up with 1,516.7 miles. Second question, you can check the math there. How much would it cost to travel 10,000 miles? So C is the cost, is equal to 10,000 times 0.3. So distance times 0.3 plus 20, and you end up with $3,020. All right, the bell has rung. That's it for 1.4 linear functions and models, writing equations and using those equations or functions to apply extension questions for this edition of Otten Math. Catch us next time when we talk about complex numbers.